All right, welcome to 2-1, and we're going to look at describing a distribution. Today is our day 1 notes. All right, so let's look at percentile. So percentile is the value with X% of the observations less than X. All right, cumulative relative frequency graph is a graph, obviously, that corresponds to the cumulative, which means the sum of, relative means percent, and then frequency is just, remember the count, so it's the percent of the counts. It goes from 0% to 100%. So that's what makes it cumulative. And then the standardized value, also known as the z-score, is the number of standard deviations from the mean and in what direction. So a negative z-score is below the mean. So that means like less than average. And then a positive z-score is above the mean. Which means more than average or above average. All right, so formulas. So here's kind of an example of z-scores over here in the right-hand corner. The mean of z-scores is 0, and the standard deviation is 1. And then this is 2, and then 3, and then to the left of the mean, this would be -1, -2, -3, because the z-score itself is equal to the number of standard deviations above or below the mean. So the formula for z-scores is the observation itself minus the mean divided by the standard deviation. So in this chapter, it will look like x minus x bar divided by s. All right, so let's look at some examples. So let's look at the stem plot of percent of residents. So that's how the problem starts, and then it talks about 65 years older and 50 states. So here's all of our data. We have a symbol down here, which means that 15, and then the bar 2 means 15%, 15.2%, okay? So we want to find and interpret the percentile for Colorado, which has 10.1 of its residents age 65 and older. So first we need to find 10.1, which is right here. So we count the number that are less than it, 1, 2, 3, 4. Divide that by the total. They tell us that there's 50 states. So in decimal world, that's 0.08. Take that times 100 to get a whole number, which would be 8. So therefore, it's the 8th percentile. So it's the number of observations below X divided by the total times 100. And then it asks us to interpret. So 8% of the states have a smaller percent of residents age 65 or older. So find and interpret the percentile for Rhode Island. All right, so first, Rhode Island is 13.9. So we look here. You can tell that there's a lot of numbers less than that, but there's not as many more than. So I'm going to count the 9, and then, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I counted from the 9 all the way down here. That tells me 10. So basically that means if I would have counted from the 8 all the way backwards, I would have got 40. So if there's 10 in front of it, that means that there's 40 behind it. So hopefully that makes sense. I didn't want to have to count all 40. I knew it would be easier to count 10. I know that there's 50 of them, so 50 minus 10 is equal to 40. So 40 divided by 50 is equal to 0.8 times 100 is equal to 80. Therefore, it's the 80th percentile. So then we interpret exactly the same as before. 80% of states have a smaller percent of residents ages 65 or older. All right, which of these two states is more unusual? So you might automatically think that it's the higher, but it's actually the one that is farther from the mean. So 8% versus 80%. So 8% is much further from 50%, which is where the mean would live, versus 80%, which is only 30 from the center. So which one of these is more unusual? It's 8%. So the 8th percentile is much more unusual. Therefore, Colorado is much more unusual since it is further from the center. Okay, so usually it's the smaller number, but it might not be depending upon what the data is. So just go with the one that's furthest from the center. All right, Coach Snyder came home very excited after a visit to the doctor. He announced proudly to his wife, "My doctor says my blood pressure is at the 90th percentile among men like me. That means I am better off than about 90% of similar men." How should his wife, who is a statistician, respond to Coach Snyder's statement? All right, so first off, sometimes being in the 90th percentile is good. In this case, not exactly. So Coach Snyder's wife should probably somehow nicely say, and this problem's made up, so don't think that his wife is actually a statistician. She might be. So Coach Snyder's wife, apostrophe S, will want to tell her husband in the nicest way possible that the 90th percentile is not a good thing. In this case. His blood pressure is higher than 90% of men like him. So basically his blood pressure is too high, and his doctor was calling him to tell him, oh, they probably need to take some medicine. All right, so Brooke is a star runner on the track team. In the league championship meet, Brooke records a time that would fall at the 80th percentile of all race times that season. But her performance places her at the 50th percentile in the league championship meet. How is this possible? So in one of them, so basically she has her time, and her time, if when compared to all of her other races that season, would be the 80th percentile, but her time when compared to all of the people running the race, the league championship, would only be the 50th percentile. So hopefully you can see that there's two separate distributions. There are two separate distributions. Right? One is her times. So she did 80% better than she did in, or she did better than in 80% of the races than she did. In terms of the league championship, she only did 50% better. So there's two separate distributions, her times and the league competitor times. Or however you want to say that, the people that she's competing against in league competitors times. So she only did better than 50% of the people when compared in that distribution of the league competitor times. Probably not good enough to win a championship or a medal. All right, so let's look at example 4, the percentile plot. Below shows the distribution of the percent of foreign-born residents in the 50 states. So the highlighted point is for Maryland. So I drew a little arrow to this so that you could see. Wasn't sure if the highlighted spot would show up or not. Describe what the graph tells you about this state. So what we do is from that highlighted spot, we're going to go directly across, and this will tell us the percentile. So it's about the 70th percentile. Right, we're just going to write that down. That doesn't really tell us anything about the context. And then we go straight down from this point. Try to go straight. It's hard to do it on this little pad. We end up right about here. So the middle would be about, what, 12.5? So we're a little bit in front of that, so probably about 12. So let's write that with the context. So Maryland has about 12%, 12.5%, or 12%, sorry. 12% foreign-born residents. All right, so now let's tie in with the context of the percentile. So about 70% of the states have less foreign residents. All right, so now part B. Use the graph to estimate the 30th percentile. So if we go to where the 30th percentile is, right, and just go directly straight across, and then go straight down from that point, we end up right about here, which looks like it's about 4. So it looks like it's about 4% foreign-born residents. And where it says explain your method, what you draw on the graph over here is actually your work. So remember that the AP test is paper pencil. So when you draw on the test, they actually grade your drawings as a part of the answer. So explaining your method is actually the marks that we put over here on the graph. All right, number 5. So the graph below is a cumulative relative frequency graph showing the lifetimes in hours. So we talked about how it goes from 0%. So you can see that it starts at 0, and if you trace along, it ends up at 100%. So these are all the, basically kind of like all the percentiles, as well as the percents along the way. So cumulative relative frequency graph is also a percentile graph. So we want to estimate the 60th percentile of this distribution. So we can see that the left side over here is percents, which means that's where the percentiles live. So here's 60%, so we try to go straight across. Easier said than done on this. Not too bad. And then you have to go straight down. and this will tell you what score it's at. All right, so that looks like it's about 1,000, right? It's somewhat halfway between the two. So we would want to say that it's approximately, it doesn't have to be complete sentences or anything like that. So it's approximately 1,000, and then instead of putting lifetimes, we're going to look and see that lifetimes means hours. Okay, so approximately 1,000 hours. What is the percentile for a lamp that lasted 900 hours? So here's 900. So this time they're talking about hours, and we're going to go up to where the percentile is. Oh, this is harder for me to do on this. All right, and then go directly across. So it looks like it's somewhere, what, about 36, a little bit more than 30. So it's approximately the 36th percentile. Okay, so hopefully that makes sense. If not, we're going to go over it again tomorrow. Just do an example. So number 6, or sorry, z-scores. All right, so over here, I put a little picture up here. You can see that 0 is at the middle. 0.5, this is a z-score of a half, and then a z-score of 1. So don't worry about the percentages in there. But notice that when it's above the mean, it's positive, and when it's below the mean, it's negative. And if you are the mean, if you're just average, then the z-score is 0, right? Because there's no deviation from the mean. You are the mean, right? So keep in mind that the closer you are to 0, the more average you are. The further away you are from 0, like the bigger, if you had a z-score of 4, that means that you're 4 full standard deviations from the mean. If you have a z-score of -4, that means that you're 4 full standard deviations below the mean, right? Which, depending upon what the distribution is talking about, could be a good thing or a bad thing. All right, so if a z-score is positive, the observations are above average or is above average. If a z-score is negative, the observation is below average. Z-scores, these are units that are measured in the number of standard deviations from the mean. So even if your data has like centimeters or something like that, z-scores don't have centimeters because what they stand for is just the number of standard deviations from the mean. So there basically are no separate units. The units themselves are the number of standard deviations. The distributions of z-scores have the same shape as the original distribution, but they will always have a mean of 0 and a standard deviation of 1. So some students think that z-scores always have to have a normal distribution, which isn't necessarily true. So it matches the same distribution as what the data came from. All right, so let's look at this last problem here. So 3 landmarks of baseball achievements are Ty Cobb's batting average. So this little guy right here is Ty Cobb. He hit 420 in 1911. This little guy is Ted Williams. He hit 406 in 1941. And this guy, probably a little bit more familiar to you guys, is George Brett. He's hit 390 in 1980. These batting averages cannot be compared directly because the distribution of Major League batting average has changed over the years. The distributions are quite symmetric, except for outliers such as Cobb, Williams, and Brett. While the mean batting average has been held roughly constant by rule changes and the balance between hitting and pitching, the standard deviation has dropped over time. So that means basically there's less variability. So compute the batting average, standardized batting average. So whenever you see the word standardized, that means z-scores for Cobbs, Williams, and Brett to see how far each stood above his peers. So let's do z-score of Cobb first. So the formula is the score, which is usually in the data. So 0.420 minus the mean, which is 0.266, divided by Cobb's standard deviation, which is 0.0371. So we put that in our calculator, and we should get 0.1415. Right? And then we do the same thing for Williams. So Williams' x is 0.406, right, his observation, minus his mean divided by his standard deviation. So we put that in our calculator, 4.26 standard deviations above the mean. And then we go to Brett. So z-score for Brett, his batting average minus the mean of his distribution, or at least the distribution during his year of playing there, 0.0317 equals. And this is supposed to be the 80s. The book had an error. So then we get 4.07. Okay, so if we look at this, what does that basically mean? So we always want to be able to interpret what all this means. So all 4 hitters were at least 4 standard deviations above the mean. So if you think of the gifted program as 3 standard deviations of the mean, this is like 4. So if we were talking about intelligence, they would be like Mensa program people. So standard deviations above the mean. So one of the reasons why they're all in the Hall of Fame, you can kind of tell. Williams' Z-score is the highest. So theoretically, he was actually the better hitter during his time. All right, so that's our notes for today.